Today we're actually going into multi-core, as opposed to yesterday looking at single core. And therefore we're going to be looking mainly at the threading model. So what we've typically done over many years since we had large machines like the one I showed before that was our flagship machine 6 years ago, we've used distributed memory models. MPI is our typical model, although there are others such as SHMEM and so on that people use. When we get onto a multi-core machine, then we have multiple cores and they share the same memory. We tend to use shared memory models because we can have certain advantages in terms of the ability to not have to reuse and reallocate lots and lots of buffers. We can improve the communication between them by doing one read and write, and we can just have a better model. So just very briefly going to now give you an overview of some threading models and then a primer of OpenMP. Now this is not to teach you OpenMP because that was said before the course began. You should know OpenMP, but just to brush up for those people who don't know it or don't know it very well. Only when looking at that on things particularly to do with parallelization of loops, not some things to do with OpenMP sections or tasks. But if you want to know anything about those, if you have any questions or if you're using them, there are plenty of people here from CSCS and other places we know of who use other models and who are familiar with OpenMP. So the first thing to look at is the operating system memory model as to what is the difference between a process and a thread. So the point about a process is there's a lot of state. Anytime that you get a process running, even if it's something as just a shell, a bash script or whatever, or even something from within shell, awk or whatever, it's going to have quite a lot of state. It's going to have some memory, it'll have file handles, possibly sockets, etc., etc. Now the operating system, whenever there's a process there, it creates completely separate state for each one of the processes. Yeah, there's no interference between the two. If there were, then we would have some serious problems. In the same way that also when a process opens a file, no other process can just suddenly randomly write into it unless it's also opened the file. Now, the other thing is that one process can't see the memory of another unless you explicitly allow it to. And explicitly allowing it to is quite complicated. You have to do something like System 5 shared memory regions and so on. So normally you don't see anybody else's memory. So memory is managed separately within a process depending on what type of memory it is as well. So there's stack memory, heap memory, text memory, etc., etc. So this means that the text memory would be where you would store your data that actually is the program execution code. So these are von Neumann architectures. They share the memory between the executable and the data for the program, but the operating system tries to keep those things separate in some way. The heap is the memory that you dynamically allocate statements, mallocs, and so on, taking from the heap that the operating system itself is managing. And then it is also a stack, a piece of memory that the process is allowed to manage. And you can change the size of the stack. By default, the stack size on Linux systems comes to be 8 megabytes. And this is often a problem when we're doing threading, particularly OpenMP threading. You often find that you get segmentation faults. And you're looking through your code and you can't find why it is and so on. And it's because memory is trying to be allocated from the stack by your process, and there isn't enough of it. And rather than actually give you some meaningful message, it just segv. Not very helpful. So therefore, often when we run OpenMP codes, one of the things we will do is we will, at the operating system level, change the stack size. So depending on your shell, it will be something such as ulimit stack size unlimited, or if you're a C shell user, I'm not quite sure, it's something like ulimit -s or whatever. You just check what your particular shell requires. I would recommend that you do that all the time, okay? Because there's really, I've asked around, and nobody seems to have a great reason why we would want to actually keep the stack size to a small amount these days. in the olden days, operating systems actually worked in a slightly different way. And if they'd given away some memory on the stack to a process, they couldn't reuse it. But as I was sort of indicating yesterday, and these days, because of virtual memory, when memory is given out, it doesn't necessarily mean it's really given out. There's no memory physically attached. It's just a record keeping. So think about setting the stack size always to a high level before you run an OpenMP code. Now, that's about processes, and multiple threads launched from the same process share the same address space. So this is now a different way of working. If one thread's doing something, the other thread can see it. Threads launched by the process share the same state information. That includes the memory. But at the point that they're launched, they can see anything that was created beforehand. So all variables that exist at the point the thread is created, in most of our threading models, can see anything that was created beforehand. However, anything that then that thread creates afterwards is typically a private variable. No other thread can see it. It doesn't know about it. That's because the thread's taken it along. It's gone and got a pointer somewhere. There's no way of it telling the other threads about it unless it explicitly does so by some communication model. This isn't true of all threading models, actually. Has anybody heard of the D programming language? OK, people at the back. Yes, OK, from CSCS. So the D programming language is a relatively new one. It's for people who were writing C++, originally wrote one of the compilers and so on, and said this is how they thought it should have been made. And one of the things that they've done is they've said that in their threading model, everything is private to a thread unless you explicitly make it shared. That actually does, in some ways, make their threading model a little easier to work with, because one of the things that we're always concerned about is scoping. And if you, at the moment, we're in the case where everything is shared and then we have to make things private, they prefer to do it the other way around. So as we can see on this model, what we have is two separate processes here. This one is a simple process. It's got some memory mapped regions, some piece for the text section, some heap, and some stack in the global address space. And of course, there's then virtual to physical mappings on top of this. But in a threading model, all these threads share the process. They all have access to exactly the same things. They follow the same piece of text. I should say that sometimes these processes, actually, the text section may be shared depending on the operating system, depending on how things work. If it sees that it's exactly the same code, then it won't, even for processes, it won't necessarily load a new version. It may keep, particularly for example, shared object libraries and so on. And this can cause a problem from time to time on a machine you're on, even if you're not using threading. One example is we have this SGI Altix machine that I mentioned, 2 terabytes of memory, 256 processors. But remember when we did NUMA-CTL, and I said this one goes from being quite close at 10 units to 50 units and 100 units. Well, one of the things actually that it turns out, and it was Jean-Guillaume at the back who discovered this talking to some people, that it does is, if it sees, when launching an MPI job, that you're launching the same executable and the same shared objects, oh, I'll just need one copy of those. But now the actual code that you're running sits in a process really far away. And actually, just to actually run the executable caused huge problems because everybody was having to spend a long time just fetching the code itself. So this caused a problem on that machine. So why use threading? So we've got a number of different reasons. A number of different people have different reasons that they want to do it. So one is just to increase the ability to get more parallelism without having to go through and do a lot more MPI coding or other distributed memory coding. And it may be easier, therefore, to do distributed memory in one fashion and then at a finer grain go down and do some threading. You may also be able to reduce the number of distributed memory tasks and reduce some communication overhead. So we're now at the position where we had, on the first machine that I mentioned when I was saying the difference between now and a few years ago, we had 1,100 processors. Sorry, 1,100 processors. we now have, if we take each core and consider that a processor, on our current flagship machine, we have 47,000 processors. The number of nodes hasn't actually gone up very much. But if we do each one as a separate processor, there's a lot of communication that all of these have to do. We can kill the network traffic. We can do all sorts of things. If we start to be able to make it so that one MPI process sits on each node, which actually, unfortunately, isn't very easy to do on that machine because of certain effects that you'll learn about tomorrow called NUMA. But if we can limit the number of MPI processes and use threads instead, we can limit the on-node communication. We just don't do it in the same way. We just read the memory. Sometimes we'll do functional parallelism. And sometimes that can be done with tasking and so on, and I'm not going to talk about that particularly today. Sometimes you can improve load balancing via constructs that enable work stealing. So one of the things that, when Ben was talking yesterday, just stopped when he was going to talk about Silk Plus. One of the things that this Silk Plus is very good at is you create a lot of threads or a lot of tasks that you want to do, and then some of those threads will go along and say, well, I finished that piece of work, I finished a few pieces of work, I'm just going to steal some work from somewhere else. And this is part of the scheduler and so on that they've done a great deal of work for to improve performance. You can similarly do the same thing if you wish with OpenMP. And the other reason, and this is a major reason, much more so than we perhaps initially thought when we were trying to first teach threading, is reducing the memory overhead so that an individual process, it's got all this memory attached to it. But rather than have lots and lots of little buffers and all sorts of other overheads with lots of processors, you just have one with all those buffers, and then the other threads don't have to allocate extra work, and you get better memory usage. So we're here talking about OpenMP. What is OpenMP? Open multi-parallelism. It's an API for shared memory parallelism, multi-threaded shared memory parallelism. There are three parts to it. Compiler directives, and these are the things that we normally think of as OpenMP. This is what we go in, we put in all these directives, these pragmas, or we put our exclamation mark $OMP ... and get ourselves some parallelism from those. But there's more to it than that. There's actually a set of runtime library routines. We've met one of them, the timer. I keep getting you to put in the OpenMP and FOpenMP, because we're getting the timer. And it's easier then, because then it will link in the library of routines, including that timer. And environment variables, and these are the ones to say things such as, how many threads do we want to run? It could be also the schedule. How do we want the loops to be given out? If we've set runtime as the scheduling strategy within our code. It can be other things. So one of the things that is sometimes significant, or certainly used to be with the Intel compiler, was OMP dynamic as an environment variable. And this would be, you can tell that runtime that you're allowed to change the number of threads downwards from what I said, if you think heuristically it's not a good idea to run with all the threads. This can sometimes cause problems, particularly with affinity and some other things, NUMA issues that Ben might talk about. It's a fork join model. So the master thread comes along, we begin with a master thread, create a parallel region, and then when the parallel region is finished, we join. And then we do this again and again and again. There's overheads to doing that fork and join. One of the things about that is that you have to synchronize at this point, stop what everybody, make sure that everybody's together, because you're closing down the other threads and you can't carry on if they've not all finished their work. If instead you were able to just have a master thread carry on and not bother with the fork join, then you can sometimes be able to get on with other work and speed things up. And these things work in a team. But often wary of the fact that some people have criticisms of OpenMP. There are problems with OpenMP, there certainly are. And there are alternative threading models. As I said, in some languages where they've got natural support for threads, such as in D, then we don't even go anywhere near OpenMP. There's no implementation for it. OpenMP is only for Fortran and C++. So one of the possibilities is to use pthreads. So POSIX Threads, an interface from the POSIX Standards Committee for threading, and a library, pthreads. So sometimes you may see with error message and so on, pthread underscore ... actually delivered to you, even from OpenMP codes. Most OpenMP implementations are built on top of it. That's why you may see these error messages. In fact, most threading libraries of any type are built on top of this because as a POSIX standard, it's easy to interface with the operating system. So typically, you will see that low level, even with things such as any thread building blocks and other things we may look at, you'll get the fact that there's POSIX threads at the bottom. pthreads has a much finer grained control than OpenMP. So with OpenMP, we're going along at a very high level and saying, parallelize the loop. Just do it. Okay, you work out where for any individual thread, where we begin, which iteration, where it finishes, all the rest. You could do the same thing with pthreads, but it becomes very complicated because now you have to go along and say, okay, for how many threads do we have? Do all the things that OpenMP is doing under the covers. You can do this. It has mutex and condition variables for synchronization. Mutex stands for mutual exclusion. So this is a special type of variable that if you go through the POSIX interface, only one of you can have access to at a time. Everybody else is excluded. Condition variables, these are variables as well where you would be going along and you want to only be able to proceed, for example, when some condition is set, when somebody else sets a condition. And these are the ways that synchronization works in POSIX threads. It's really low level. So the disadvantages compared to OpenMP, well, for the probably 40% of people who put their hands up to their Fortran programmers, this isn't even an option anyway. And this is typical of actually most alternatives to OpenMP. There was once a Fortran interface, but it was specific to a compiler. As I said, you have to manage all that work sharing yourself. Where do I begin? Which iteration of a loop, etc., etc. And this means that the code becomes very, very large for normally no real advantage. It's very low level, as MPI for our distributed memory is often referred to as the assembly language of distributed memory. pthreads is very low level as well. And you'll typically take many, many more lines of code for pthreads than OpenMP. So OpenMP is about productivity for our numerical codes as much as anything else. It may be, in some circumstances, that you could get much better performance out of pthreads if you really know your algorithm. But that's true about any algorithm where you know the algorithm, so you know how things work. You can normally do a better job than a high-level approach. But productivity-wise, when you've got hundreds of thousands of lines of code or something and you wanted to go through, you want simple tools, which we'll see in about an hour and a half's time, and you want to be able to just do this so you can go through and parallelize everything. After all, remember, Amdahl's law is our killer here, and if we don't parallelize as much as possible, then we're not going to get the speedups that we hope for. A second alternative, again, Fortran programmers can stop listening for a while. So Intel thread building blocks. This is a C++ template library, and it adds parallel programming for C++ programmers. So no C programmers, no Fortran programmers here. There are a set of parallel keywords, and these include things such as parallel for, reduce, parallel while, etc., etc. They actually aren't real. There's no change to the language. It's just a different way of. It's all just standard C++. It's just a set of templates that you use, but it looks like it's a new language. And then you rely very much on the compiler doing a very good job of making sure that this works, this is turned into good threaded code. And at the low level, it will be doing pthreads, but it will be doing it hopefully quite efficiently. Now, because it's a standard library, it's not actually any change to the code. You can take any of your C++ compilers and actually use thread building blocks. So you can buy a copy of TBB from Intel, or you can get a free version. So there are all these other things that you can use, like containers, locks, and task schedulers, and so on. Now, naturally, this is being a template library and quite a complicated one. You can go and put it with your C++ compiler, but it might not work very well. So using the Intel compiler would be the best option. Now, the interesting thing with TBB, why is it there, where does it come from, and so on, it was actually built out of positive user experiences from OpenMP. This is from Intel, and Intel provide a lot of the people on the OpenMP Standards Committee, a lot of the people actually doing the administrative work and so on and so forth. And a lot of people in Intel are the leaders of OpenMP and pushing it forward. So therefore, for them to take something and say, well, we see some places where for C++ programmers, there may be some advantage to provide a different interface, and that's what they did. So they could provide something that was an object-oriented, template-based approach that people who program in C++ might feel more comfortable with. So what about TBB versus OpenMP? As I said, this is Intel after all. And it provides many members, directors, officers, etc. of the OpenMP forum. And so what I put up here, I've been putting on slides for a couple of years now, and then last June, we heard there was a course held here, and a couple of people from Intel were along. And one of the people who's very prominent in parallel programming, you can see his writing articles on HPC Wire, etc. Of course, James Reinders. I said, well, this is what I say. Is it true, or have I just taken something from the website and so on, which isn't necessarily true? He said, no, he agrees with all of this that I put up now. So the first one is a statement, and this is all from the TBB website, okay? So this is if you go to a car salesman and say you want to buy a Porsche, and he tells you something, like go to the next showroom, then okay, I'll go to the next showroom and buy the car that you're recommending, it's probably better. He said everyone should use OpenMP as much as they can. It's easy, it's standard, it's supported by all the major compilers, exploits parallelism well. Okay, so everyone should use it as much as they can, even if it's not very beneficial. OpenMP is the standard way to do parallelism in C and Fortran. Of course, TBB is C++, so therefore it's not making a statement about C++ there. Now, then it comes down to when you should use OpenMP and when you should use TBB or some other programming model. And this actually doesn't necessarily only apply to TBB, but it could equally apply to maybe the times you might want to go on to pthreads and so on. If a parallelism is for bounded loops, built-in types, do loop-centric, the sort of stuff we were talking about is what makes vectorization good. Regular data, just doing the same thing over and over, and particularly well load balanced, then that's when you should use OpenMP. Performance-wise, it can be very challenging to match OpenMP performance with TBB for these types of problems, because people have optimized this into the ground to really make this work well. It's seldom worth the effort to bother. After all, remember we said that this was about productivity as much as about performance, so just use OpenMP. And so we have in the building some people who really do like C++ and going for some really complicated aspects of it, and often either for reasons of simplicity for other people getting their codes, after all we want maintainable and readable codes, or just because of the way that it's implemented, even they would use OpenMP over TBB. Should you expect TBB to outperform our standard models? No. It may offer a competitive alternative, but it exists to do different things. Particularly, for example, tasking. The tasking model in OpenMP exists, but it may not be as good as the tasking model in C++, in TBB for C++ programmers. And so OpenMP and MPI continue to be good choices. TBB also was not designed primarily to be used in high-performance computing, but was more to be able to get the sort of multi-core improvements just on a desktop or similar. And particularly also when you go beyond the straightforward data parallelism that typically in high-performance computing we're interested in, and you go on to more things such as task parallelism, or you might be interested in work sharing or similar. So if you don't fit the standard data parallel model, you may wish to look at TBB, but we're going to be talking here about OpenMP. One of the tools should say, so you're going to see reveal, the Cray tool, shortly, and we mentioned that this is just one example of a tool. You could go along to the Intel site and get similar tools, and there they have something called Advisor, and this helps you to parallelize your code. Because Intel support OpenMP and TBB and other programming models, if you use that tool instead, when you actually do this annotation of loops, I want to parallelize this region, you can choose to use TBB instead if you're doing C++ program. And note also that they can coexist. Ultimately, at the low level, they're all using POSIX threads. It might be a little difficult to get them to coexist, but they should be able to do this. So why do we use OpenMP? It's ubiquitous. It's everywhere. GCC provides support, so therefore it's everywhere. That's the thing. If GCC supports something, fine. You can get a compiler for it. And you don't even have to pay. So, and the one we're using recently, 4.7, supports the full OpenMP 3.1 standard. There are vendor-tuned implementations available, but actually, and so each vendor will provide its own library with its interface. And some of them may have played around a little more than others in terms of how they allocate memory, how they retain memory, and so on, to try and get you some better performance. And that's something that Cray do, particularly on the machines that we've got, so they try not to give memory back if they don't need to. It's an easy interface. So people have used OpenMP here. It's not something complicated. You can parallelize very quickly. It's not like even MPI's tried to be easy, but there you have to go along and do a lot more work. It is the best fit for data parallel codes. Don't take my word for it. Take the TBB website's word for it on that basis. And it is being updated all the time. So the task parallel features are added in OpenMP3. They're not brilliant, but they're there. We're looking to possibly get accelerated directives in OpenMP4. Maybe that might slip OpenMP 4.0. But you were hearing yesterday about the SIMD directive to try and incorporate parallelism from threading and vectorization at the same time, and that is being targeted for OpenMP4. So they're trying to always make sure that there are simple keywords that you can add that will improve your parallelism. Okay, so that's about threading. What about actually OpenMP itself? This is where now I'm just going to go reasonably quickly through a review of OpenMP, because so a couple of people said they weren't necessarily completely okay with OpenMP, but most people here, it was down as one of the prerequisites, so therefore we assume you know this sort of stuff. And this is the standard set of slides, but just cut down than what you may have been if you've been here at a summer school or something. First, the most important thing is, if you don't know anything, the one thing about OpenMP, another great feature of OpenMP is the documentation. You get hold of the standard, you've got lots of examples, about 140 pages of code examples in the standard. And it's free. You just get it off the OpenMP forum website. So there's more, I think, in terms of examples in that standard than there is actually to describe the standard. So let's jump straight in and say, how do we create parallelism in OpenMP? Parallelism is specified using these compiler directives, C, #pragma-omp, and Fortran, $OMP. This thing is called a sentinel. Don't know why that word's used, but we refer to this sentinel. That has to begin anything if you want to do something with OpenMP. You have to be careful because, for example, there's things you can find of common problems that you might encounter with OpenMP. Somebody may forget to put OMP on their pragma line, and depending on whether your compiler complains too much about pragmas, you may quite happily ignore it and just not give you the parallelism. Make sure you've got the full thing in. So you can just add directives. You don't need to use anything with the library, etc. The scope of directives. So what is the defined region over which the directive will work? In C, it's the next block immediately following the pragma. So I recommend you should always put curly braces around the region you want to be parallelized. In Fortran, we put a parallel and an end parallel session, or a do end do session, etc. Here I'm assuming that we're all actually after 1990 in our Fortran programming as well, and that we understand that we use free source form. Threads are created with the parallel directive. So outside of the region, there is only one thread, the master thread. It is, if you've compiled serial code, you've still got that one thread running through. It's the master thread. Inside a parallel region, we'll have n threads, whatever n happens to be. The end of a parallel region, there's an implicit barrier. Everything has to finish before we close down the region. Simple example of the parallel directive, whichever your preferred language happens to be. We hit the parallel region. In here, we've declared from our scoping that ID is private to the thread. We can get a thread num, we can get the number of threads, and call some variable. Interestingly, you should read the interfaces for these functions, by the way, because sometimes they behave differently depending on whether or not you're in a parallel region. So get thread num, for example, if you happen to call it outside, well, it's only ever going to be the master thread. The num threads may differ as well as to whether it sees that there are a number of threads actually active or not. So always make sure you're in the right region. So we have these runtime library routines. Get thread num, get num threads, and the number of threads in the team. And as I said, you need to check whether or not, for your implementation, threads in the team actually says currently active threads in the team. And that may therefore differ also if you're doing nested threading. We've met OMP get W time, returns a double precision number in seconds. I often compile codes with OpenMP flag just to get hold of this routine, either this one or the MPI routine, because they're easy just to say, I want this many seconds. Whereas if you try and use other routines, particularly in C, then you have to go along and start playing around with different structs and so on. It becomes a little too complicated. So there are a lot of these routines. These are the most common ones you'll come across, but you can find others. How do you access these routines? omp.h to include the header file. omplib as a module in Fortran. You can also get a header file in Fortran, but we're sitting in the Fortran 90, 95, 2003, and 2000X era, so we shouldn't be doing that. Now, one of the other things you may wish to do is have conditional compilation. So sometimes there are pieces of code that you only want to be running if you're in your threaded region. And so we can do that in C and C++. It's a straightforward using a macro, which is _OpenMP. And this will only then get compiled in if you're actually compiling with OpenMP. So in other words, if you set the OpenMP flag on your compiler, it will set this macro to be active. In Fortran, we've got a slightly uglier way of doing things, and that is $! So it's a comment, and I'm not particularly a fan of this because it doesn't really tell you that it's anything related to the OpenMP part. It could be that you just somebody randomly puts $! as something at the beginning of a comment line, and then things would start to try to be compiled by the compiler. But anyway, we do have this option of having some way of saying only compile code in if we're in our OpenMP region, and this is something you may wish to use. And by having these things as conditional compilation and all the rest, it means we can have a code which we can be OpenMP parallelized, but if we just switch off the OpenMP flag, we've got a perfectly good serial code, and it will work as intended on a serial machine. I should say, yes, it doesn't have to actually be in a parallel region to be compiled. The compiler is not detecting, it's not doing a semantic check as to where you are when you're looking at if-def OpenMPs or $! And that means, for example, you can declare variables at the beginning of a subroutine or whatever that you only are going to use if you're in an OpenMP region. In order to compile, how do we do this? Well, we saw yesterday when we were just grabbing the OpenMP timer, these are the compiler flags. The Cray compiler is one which you'll be meeting when you look at Reveal. The Cray compiler is a compiler for high-performance computing. So it's actually taken the opposite view of the other compilers. It's saying that if you put some OpenMP in there, I'm assuming you're going to be using it. And you tell me if you're not going to don't actually want this to be an OpenMP-enabled code. So you have to do the opposite. You have to turn off OpenMP by giving it this, this compiler flag. So we looked at GNU and Intel. We also have the PGI compiler on most of these things. And -MP tells you to do, tells it that you want OpenMP. And then we also want to often switch off Numa in this case, because it's being imposed by, for example, on the Cray. We also have mentioned before Open64 or the Pascal compiler. We do have a Pascal compiler, I think, still sitting around our Crays if somebody wants to try this. But the Open64, this is what you were asking about yesterday, about what AMD do for a compiler. Well, they took that, and this should work as long as you've got the OpenMP-enabled version of that compiler. Launching a job, we have to say how we want that job to be launched, how many threads we're actually going to use. And so this is the most common environment variable you will come across. It could be the only one that you're actually ever interested in. OMP num_threads environment variable. That controls the number of threads. So to run 8 threads, it's quite simple. Now, on the Cray machine, you also need to make space for these threads. What we mean by that is that the Cray, because it's a high-performance computing environment, it starts to automatically impose certain things when it sees threads being launched. So you'll meet Numa and Affinity tomorrow, but what we were saying about before, where we have a process and we have a memory locally, or we could have to go to a remote memory, etc. The Cray wants you to be going locally. So it says, once I've given you some memory, I want you to stay where you are. Don't go wandering off as a process, because processes can sit anywhere. Yeah, the operating system will move them around. But you can actually say, don't move this process. On the Cray, it goes further and says, don't move a thread. So it intercepts at launch time and at thread creation time, the thread creation mechanism to say, aha, thread created, I'm putting you on that core, you do not move. In order to therefore be able to use more cores than in a sufficient number of cores, you have to tell it how many to make space for. So we have to give it this -D flag as well as OMP num_threads. Otherwise, what it will start to do is it will say, well, for the process, I'm only giving you one core. And when you create new threads, I'm putting it exactly on top of each other. Okay. If you make space, it will round robin. It will start to put them on the other cores, and then if you happen to have said, I've only got space for 4, but I'm creating 8 threads, it will then come back and start wrapping around again. So back to directives. The master directive, as well as the parallel directive, this combination works very nicely, either master or single, to be able to allow you to set up a parallel region and not have to tear down the threads. Remember the fork join model we talked about? And there's a cost associated with firing up the threads and breaking them down again. Modern OpenMP implementations don't destroy the threads. They effectively put them to sleep, expecting that you're going to want them again. So the thread creation overhead and the destruction overhead is not as bad as it used to be, but we can still see it being very, very bad if we go to pathological cases. But here, with a master or a single, you don't actually need to tear down the threads anyway. You can just get it to do things only on one thread. So here, everybody can get their thread num, but only the master's going to print it out. So the single directive is the opposite, but now it doesn't necessarily have to be the master thread, thread 0, that will do this. So the same thing as we saw before, but now it may not be my ID equals 0, it could be my ID equals 3, whatever. Now with single, otherwise, if you don't put no weight in, then you will have a barrier actually even at single itself. So single, typically you would want a no wait in there. Critical is for those times where something is critical. You don't want somebody else to be doing something at the same time. This can often be, as related with atomic, it can be when you're going to update something, for example, updating a variable, or typically that's with atomic. So you'll say, if anybody else comes and interferes here, I could have a real problem. One example of this is actually with printing statements, where if you don't necessarily get things correct, you could have half of a sentence printed, then somebody else comes in and does their sentence, then you get the other one, and your output gets all mangled, and sometimes you don't want that. It depends very much on the implementation and thread safety of your I/O libraries as to whether that would happen or not. So with a critical, only one thread can be executing at a time. So it doesn't say anything about any ordering, but it does mean that there will be printed one at a time. So 6 threads, 6 print statements. Now, one other thing about the critical as well is, if you write a very large code with a lot of critical regions, only one of them will be in any critical region at a time. Okay, so this can produce some big serialization. If you have 100 critical regions and different threads are wanting to go into different ones of those, they will all be blocked apart from only one at a time. How do you stop this? Well, critical actually also takes an optional name. And if you have a named critical region, then that says, aha, no, it's only this named region that I'm going to stop people going into. You can still have the same name in multiple parts of your code. For example, if you wanted to protect some variables in different parts of your code, you can do so. And you should consider doing that if you start to get a lot of critical regions. Otherwise, you could slow your code down. Barrier directive, sometimes you need it. Sometimes you need it particularly if you have data that you need to be synchronized and everybody can see the same copies of variables. So it requires all threads in the team arrive at that barrier before they continue. So foo1 must have been completed by all threads before foo2 can begin in this particular case. The atomic directive. So atomic is used to protect memory locations. So in this particular case, this is to avoid something that we'll see tomorrow called a race condition. And this is basically to say that I want to update this variable n, but I don't want to be in the position where I read in n, somebody else reads it in, I update it, and then somebody else updates it, but didn't know that I'd updated it in the meantime. So atomic is there to protect an update of a variable so that only one person can do it at a time. So it's like critical, but atomic is much more lightweight. There are only a set number of operations you can do, and they're ones like this, where it's just take a variable, quickly do something to it, and put it back. Critical, you can have very big regions if you wish, particularly if you're going into something like a print statement. This is not for print statements. This is only for updating individual variables. So, in terms of speedups, the warning is try to avoid using any of these synchronization directives, because they will slow everything down. Everybody has to sync. Similarly, critical regions, if you find you're using a lot of them, start to name them and make sure the names match so that you still get the right results, but you don't slow down your code too much. So possible, try to find ways of actually avoiding synchronization algorithms. Use some temporary variables for et cetera, if you can, to get around synchronizations, around barriers and so on. So those are the directives that we would use to say how we actually want our code to be parallelized and the places that we want to be critical and so on. There's another one that we'll see called ordered that also comes into play, but mainly we're interested in parallelizing our code just using those directives. We have then some data scoping. This is then the most complicated part normally of what you actually have to do in your threading. Okay, so just going in and saying, I want to parallelize these regions and put in some for and do directives and so on, it's quite simple, but which variables are shared, which variables are private, and so on and so forth. So private and shared are the main things that we're interested in. So a shared variable is one that is accessible by all threads. As said before, if you want a variable to be shared, it has to be declared before you actually create the threads. Otherwise, they can't see something that's created afterwards. So shared variable accessible by all threads. All threads can interfere with each other. Private variables accessible only by the current thread. Any variable that is declared in a region after a thread has started is going to be private. But some of those variables that are already existing, you may want to say, actually, I want private copies for everybody. Loop counters are automatically private when we do for loops, do loops, and so on. We also have first private and last private. And we're declaring here what the default could be. We can also say we don't want any defaults. We want you, when you actually go around and say a parallel region, to have to explicitly say whether a variable is private or it's shared. So you can say that, look, assume all that my variables are private unless I tell you that they're shared. That would be effectively having the same model as what I said the programming language D would have. Or its default is shared, which is more typical, and then you have to explicitly say the private. If you have the opportunity, it's much better to do default none. But it does become very tedious if you have to go through and declare every single variable, and there's a lot of them in certain regions. So typically, a lot of people back out, pick one of the others. So some private and shared data. So you're declaring individual variables here. X0 and Y0 are private variables in this particular example. A bit of Fortran for those C programmers. And so we have a couple of arrays, and we just happen to take a couple of values from those arrays. The arrays themselves are going to be shared because we haven't said that they should be default none or whatever, but we could declare them as being shared. Down here, we've explicitly stated that they're shared variables. If we could put in default none, we would have to do this notation. Now, sometimes we want variables to be private, but we want them to come in with the value that they had if they were in the serial case, or with the value that they had before we launched a parallel region. In that case, we have the first private directive. Variables are now private, but they're set to the value that they had beforehand. So A inside this region will have no value. It is whatever the default value is. It could be 0, it could be 374, it could be infinity, it could be set to a nan. B, on the other hand, is first private. B will, for each of the threads, have the value of 2. It's a private variable, but it will be set to 2. Now the point about this, one of the aspects of this is that if you happen to set this in for arrays as first private, then it has to make actually not only a private copy of the array, but it has to now physically go through and set the values all over the place. So you wouldn't really want to do that unless you absolutely had to. Last private does sort of the opposite. Okay, and what I mean by sort of the opposite is, well, with first private, it's fine. We take what was there before and give it to everyone. But when you close down, you want to say, right, I want a value to be given based on what we've just calculated in the parallel region. I want a value to be given outside of the parallel region to a variable. Well, we've got multiple threads, and they could all have completely different values of this variable. So which one do we give the value to the master thread? Could be that it's thread 0's value. It could be all sorts of things. Last private says, if you have a loop, it is whoever did the last iteration. Whoever did the last iteration of the loop, that's the one that we set the variable to be. So on this particular example here, A is just being set to these values. A will come out to be 1,000. Okay? So we're now back into, now we understand private and shared variables, we can now go in and actually look at the most important of our work sharing constructs, and that is when we give out loops, and when we start to divide up loops. And that's do in Fortran or for in C. So we have a simple do loop, would be a for loop, of course, in C. By simply putting OMP do, we have now parallelized that loop. If we have 4 threads, we go along and we say from 1 to n over 4 effectively, or it could be n over 4 minus 1, will be given over to the first thread. And then beginning at n over 4, for the next set of iterations will be given over the next thread. This thing's getting divided up. OpenMP will determine how much work it should give out to each thread by default by dividing them by the number of threads. But you can control this. The other important thing, not in this case, because the parallel region ending means that all the threads will get torn down anyway, but if you have a larger parallel region with separate do loops, putting no weight on can be very valuable if the next piece of work does not rely on those iterations all being completed. Now, for convenience, the two statements can be combined, and that's what we will see from reveal, I believe. That is correct? Yes. Typically, yes. So this will allow you to get the parallelism that you're looking for. Unfortunately, it means that every do loop, you close down the parallel region, and if there's not enough work to do in the meantime, then that will start to introduce an overhead. Reductions. So very often you'll need to compute a variable that may be, for example, the sum of a set of values. Or it could be that what is the largest of a set of values coming out of a loop. And that's something you can do in Fortran, but not in C. In this particular case here, we have a standard serial loop, and we're trying to calculate the average. Now, if we divide this up amongst a set of threads, during the loop, each one of them is going to get a separate copy of this average variable. And it's only going to be one quarter of the final sum. Okay? Not necessarily exactly the value 1/4, but it will continue one portion of the final sum. And then we want to divide at the end. This isn't something that is therefore normally easy to deal with. But what we have is we have a reduction clause in OpenMP that helps us out of this area. Because otherwise we're going to have to take our parallel region, get all of these averages one by one, take a separate variable, have a critical section or an atomic to update some other variable that then goes into a last private, and then the master thread could actually then do the division. That's messy. We don't want any of that. So what instead we have is something here. We now can get rid of that last piece and so on. The summation now is done by OpenMP itself. Each one of these variables will be set to be 0. We'll then be able to update individually those separate sections, and then when that do loop is finished, it will then sum up average, and outside of that region, then average will contain the sum. It's not the average yet. We've still got to do the division. So the two things here, as I said, it's automatically declared private for each of the threads during the do loop. It's automatically set to 0 in this case because we've said it's a summation we're looking for. And then outside of the loop, it will be set to the summation of all the individual private variables. So we have this thing where we can have different operators. It's not just for summations. We can do this for other things. And depending on the language we are, whether we're Fortran or we're C or C++, we have different capabilities depending on what you're normally using in those languages. And so here's the most common reduction operations that we're able to get away with. So Some of the important things to note are that in Fortran, you can get min and max numbers, but they're not available in C or C++, which is a bit of a pain, because you therefore have to hand code your own. And so on forums and so on, when discussing C and C++, there's a few times you'll see, periodically you'll see people discussing, when are we going to get a min or a max? Okay, why are we treated like the bad cousin or whatever? And so then you get a bunch of other things. In C and C++, it's more likely you'll be using these operators than over in Fortran, so therefore you've got reductions over there. The common ones that are common to everyone, though, are your plus, your multiplication, your subtraction. So that's our reductions. Now, the other thing that you sometimes do need to do, even if you've got a lot of work, is sometimes you do still need to do something in order. So if we have something that we really do need to do in order, and of course, this is definitely one of those things, as we saw yesterday when doing vectorization, there's a dependency in here. We have to do it in order. If you tried to do this without doing the order down here, OpenMP would quite happily divide that up in parallel for you. And let's say you had 2 threads. The second thread will begin n over 2 or n over 2 plus 1 equals 2 times an, even though an has not yet been updated. Doesn't care. So you have to then say, well, there's a dependency in here. I have to deal with this. I have to put the ordered in. First thing is you have to actually tell OpenMP on the do loop that get ready. I'm going to give you a piece of this code. Some piece of this code needs to be done in order. Not the whole loop, but just some piece of the code. Therefore, this is only really useful in 2 instances. One is if there's only a few iterations normally, but there's a lot of work to be done in there. And there's only one little piece of them that you actually need to, therefore, do a synchronization and stop and do this in order. You can do all sorts of other things in parallel. And if this, in this particular case, this, for example, is a matter of 1 clock cycle, 2 clock cycles, that sort of thing. If before it you had something like a matrix LU decomposition on your own private variables or whatever, you could all do those independently. Then when you finish them, you just do something in order, and then you can do some more work. So ordered can be useful at times there. You don't see it very often. The other time that it can be useful is it's one of the tricks that we can use to try and track down race conditions. Because if you do things that are in ordered and you effectively say the whole thing in the loop is ordered, you've serialized it. And so therefore you've taken it back to what the serial version would be. And sometimes that can be useful, and you can move the ordered bit around and then try and track down your bug. Now we haven't seen what race conditions are yet, and we'll see that tomorrow, but they're things that can be difficult to trace, and so therefore this can be useful for us, not for its original purpose. So scheduling. So when a do loop is parallelized, we said before that by default, what we're going to do is we're going to take these iterations, say 100 iterations, 4 threads. You get the first 25, you get the next 25, and so on and so forth. But that's not necessarily always the best way of doing things. It may be, for example, there's poor load balance in the amount of work that's done in each of the threads, in each of the iterations. And therefore, if the early ones have more work to do, then it's going to be not a very good parallelization strategy. So therefore, we have a set of different ways of doing this scheduling. The schedule directive, or the schedule clause, sorry, I should say, allows you to specify how you want this parallelism to be done. There are 4 possibilities. Static, which is the default, but even then you can change the way that static works. Dynamic, guided, and runtime. So the schedule clause accepts 2 parameters, and we'll go through what the different things are, the static and the dynamic and so on. So you say the type of things, and we've seen static, dynamic, and then the chunk size that you want. If you leave the chunk size off, it takes its defaults. So what do these things actually mean? Static, which is the default. If you don't do anything, it's as I've mentioned. You take as many iterations there are, you just dish them up into chunks, and then you get on with the work. But if you specify a chunk size for it, then what it will do instead is, for example, where we had 100 iterations, and we had, we said by default it would give out with 4 threads, 25, 25, 25, 25. That's probably the best way of doing it. If instead you said that you wanted static 5, it would say the first 5 iterations go to the first thread, the second 5 go to the second thread, and so on. And then that will take us up to iteration number 20. And then it will give the next 5 out again to thread 0 and so on. So it's more in a cyclic fashion. It will go through and give out the threads. If you get the 5 might be a reasonable number, because you're still giving out 25 threads to 25 iterations to everyone. If you said instead that you wanted it to be 10, that would be a worse number, because then you would have some of your threads getting 30 iterations, some getting 20. So you have to be careful when you specify this. Dynamic is where a set of threads are given out at a time, and then it may be, for example, you say you want to give out 10 threads to each of the different threads. So that would then begin as normal. 10 threads to the first thread, 10 threads to the second. And then who gets numbers 41 to 50 of our iterations, or 40 to 49, depending on your language, it's the first one to finish. First one to finish will just come along and then grab the next bunch of threads. And the next one will grab the next. So dynamic can be useful if you really don't know how much time a particular iteration is going to take. Faster threads get more work, slower threads get less work. When we say faster and slower, we're not in terms of the clock speeds or anything here. Normally we're talking about threads that simply had less to do in their iterations, so therefore they're faster to get their work done. And so then the final two, we have guided. Now, guided is like dynamic, giving out big chunks of work, but it gives out big chunks to begin with, and then it shrinks down the next time how much is given out. So it may be, for example, that we say we have 100 iterations to give out. I'm going to give out, to begin with, everybody gets 15. That's 60 of our iterations given out. We've only got 40 left. And then it may be, well, the next time we're going to give out, say, 6 to everyone. So now we've got another 24. We've still got some left. And this can be also quite useful, like with dynamic, but you start out with big, bulky sections that people can get a lot of work to do. It means you might have to come back fewer times to keep grabbing a certain number of threads. And it also means that as it shrinks down over time, you're less likely to end up with one of the threads just slightly finishing ahead of the other, getting something to do, the other one gets nothing to do. You'll get some finer grain. You don't want to set the chunk size too bad, but you also want to keep synchronization down. And the final one that you might want to set is runtime. And then we have an environment variable that we set, which we can then vary at runtime for what that scheduling should be. So by default, it's going to be static, but we can specify both of these just in a string. And every time you come to a variable that's been set schedule runtime, it reads that string and decides to give out in that particular fashion. Now, one thing you therefore will note is that we have only one of these for an entire run. That is, every loop that you put on that you're going to do schedule runtime will have exactly the same schedule. It's not that you can say, schedule runtime for this particular loop, I want that variable to be read. This one, I want that variable to be read. Unfortunately, you're stuck with one. But it can be quite useful. So, as I said, I'm not talking about anything like sections or tasks. Those are other aspects of the OpenMP standard that we might want to be interested in and might want to look at, and you might find more useful. Although if you're in those sort of things where you're looking at, say, tasks, it may actually even be, if you're not a Fortran programmer or a C programmer, but a C++ programmer, you might want to look at one of the other models. But here, this should give us all the ammunition we need for the next day or so while we're looking at using some tools to be able to enable us to do the parallelism. Because what we're concentrating on mostly is loop-based parallelism. Threads launched by the process share the same state information, that includes the memory, but at the point that they're launched, they can see anything that was created beforehand. So all variables that exist at the point the thread is created, in most of our threading models, can see anything that was created beforehand. However, anything that then that thread creates afterwards is typically a private variable. No other thread can see it. It doesn't know about it. That's because the thread's taken it along. It's gone and got a pointer somewhere. There's no way of it telling the other threads about it unless it explicitly does so by some communication model. This isn't true of all threading models, actually. Has anybody heard of the D programming language? Okay, people at the back, yes, okay, from CSCS. So the D programming language is a relatively new one. It's for people who were writing C++, originally wrote one of the compilers and so on, and said this is how they thought it should have been made. And one of the things that they've done is they've said that in their threading model, everything is private to a thread unless you explicitly make it shared. That actually does, in some ways, make their threading model a little easier to work with, because one of the things that we're always concerned about is scoping. And if you, at the moment, we're things to do with OpenMP sections or tasks. But if you want to know anything about those, if you have any questions or if you're using them, there are plenty of people here from CSCS and other places we know of who use other models and who are familiar with OpenMP. So the first thing to look at is the operating system memory model as to what is the difference between a process and a thread. So the point about a process is there's a lot of state. Anytime that you get a process running, even if it's something as just a shell, a bash script or whatever, or even something from within shell, awk or whatever, it's going to have quite a lot of state. It's going to have some memory, it'll have file handles, possibly sockets, etc., etc. Now the operating system, whenever there's a process there, it creates completely separate state for each one of the processes. Yeah? There's no interference between the two. If there were, then we would have some serious problems. In the same way that also when a process opens a file, no other process can just suddenly randomly write into it unless it's also opened the file. Now, the other thing is that one process can't see the memory of another unless you explicitly allow it to. And explicitly allowing it to is quite complicated. You have to do something like System 5 shared memory regions and so on. So normally you don't see anybody else's memory. So memory is managed separately within a process depending on what type of memory it is as well. So there's stack memory, heap memory, text memory, etc., etc. So this means that the text memory would be where you would store your data that actually is the program execution code. So these are von Neumann architectures. They share the memory between the executable and the data for the program, but the operating system tries to keep those things separate in some way. The heap is the memory that you dynamically allocate statements, mallocs, and so on, taking from the heap that the operating system itself is managing. And then it is also a stack, a piece of memory that the process is allowed to manage. And you can change the size of the stack. By default, the stack size on Linux systems comes to be 8 megabytes. And this is often a problem when we're doing threading, particularly OpenMP threading. You'll often find that you get segmentation faults, and you're looking through your code and you can't find why it is and so on. And it's because memory is trying to be allocated from the stack by your process, and there isn't enough of it. And rather than actually give you some meaningful message, it just segv. Not very helpful. So therefore, often when we run OpenMP codes, one of the things we will do is we will, at the operating system level, change the stack size. So depending on your shell, it will be something such as ulimit stack size unlimited, or if you're a C shell user, I'm not quite sure, it's something like ulimit -s or whatever. You just check what your particular shell requires. I would recommend that you do that all the time, okay? Because there's really, I've asked around, and nobody seems to have a great reason why we would want to actually keep the stack size to a small amount these days. In the olden days, operating systems actually worked in a slightly different way, and if they'd given away some memory on the stack to a process, they couldn't reuse it. But as I was sort of indicating yesterday, and these days, because of virtual memory, when memory is given out, it doesn't necessarily mean it's really given out. There's no memory physically attached. It's just a record keeping. So think about setting the stack size always to a high level before you run an OpenMP code. Now, that's about processes, and multiple threads launched from the same process share the same address space. So this is now a different way of working. If one thread's doing something, the other thread can see it. Today, we're actually going into multi-core, as opposed to yesterday looking at single core. And therefore, we're going to be looking mainly at the threading model. So what we've typically done over many years, since we had large machines like the one I showed before that was our flagship machine 6 years ago, we've used distributed memory models. MPI is our typical model, although there are others such as SHMEM and so on that people use. When we get onto a multi-core machine, then we have multiple cores and they share the same memory. We tend to use shared memory models because we can have certain advantages in terms of the ability to not have to reuse and reallocate lots and lots of buffers. We can improve the communication between them by doing one read and write, and we can just have a better model. So I'm just very briefly going to now give you an overview of some threading models and then a primer of OpenMP. Now, this is not to teach you OpenMP because that was said before the course began. You should know OpenMP, but just to brush up for those people who don't know it or don't know it very well. Only when looking at that on things particularly to do with parallelization of loops, not something